what's the plan?
And we're trying to get everything consolidated and get a cohesive set of questions to ask you.
Roger, 15, we copy. That sounds real good. Appreciate it.
Anything else to report?
Well, we haven't talked about landing for several days.
Believe none of what you hear, question everything you see.
That's affirmative. That's affirmative.
Welcome to Rich Planet TV. I'm Richard D. Hall. Now, if you haven't seen the previous show, number 314, I suggest that you watch it first in order to get some context for what is to come. I'm going to describe a project involving the design and build of an experimental homopolar generator in order to investigate the claim as to whether a homopolar generator can produce more electrical power out than the input power required to produce it. I apologise if this show appears like a physics or an engineering lesson. I have done my best to make it simple to understand, but it is necessary to include technical details in order to explain exactly how the results have been achieved. Please feel free to send me your comments, observations or critique. Now, firstly, just a note about safety. Do not try and replicate any of this unless you know what you are doing. Working with electricity is very dangerous, and this machine consists of a 9.5 kilo, 3000 RPM rotating flywheel, which could be deadly. So don't try this at home unless you know what you are doing and have considered carefully how to do it safely. So what is a homopolar generator? According to Wikipedia, a homopolar generator is a DC electrical generator comprising an electrically conductive disc or cylinder rotating in a plane perpendicular to a uniform static magnetic field. A potential difference is created between the center of the disc and the rim or ends of the cylinder, with an electrical polarity that depends on the direction of rotation and the orientation of the field. It is also known as a unipolar generator, a cyclic generator, disc dynamo or Faraday disc. The voltage is typically low, in the order of a few volts in the case of small demonstration models, but large research generators can produce hundreds of volts, and some systems have multiple generators in series to produce an even larger voltage. They are unusual in that they can source tremendous electric current, some more than 1 million amperes, because the homopolar generator can be made to have very low internal resistance. Also, the homopolar generator is unique in that no other rotary electric machine can produce DC without using rectifiers or commutators. So let's come on to the N machine named by Bruce de Palma. This is a version of the homopolar generator where the magnetic field is generated using a magnet or magnets fixed to and rotating with the conducting disc, known as co-rotation. As explained in the previous show, rotating the magnets with the disc still produces an output voltage and allows for a stronger field through the disc because the magnets are actually attached to it. My machine is intended to be a smaller, simpler version of Bruce de Palma's N machines, so I named it the Mini N machine. During the design and build process, I changed various aspects of the design as the machine was being constructed, and I will explain all of this shortly. I'll first run through the specification of the finished Mini N machine. It has a lower base plate made of mild steel. This is 350 millimeters square, 20 millimeters thick, and it has tapped holes to incorporate fixing bolts. It has an upper base plate made of wood. This consists of 2 layers of scaffolding board and is 350 millimeters by 450 millimeters and 75 millimeters thick, bolted to the lower base plate. There is a mounting block made of wood. This consists of 18mm thick panels arranged in a box structure, 170mm wide by 200mm high, with an 80mm section cut out to house the rotating discs. It is reinforced internally with more wooden block sections. The copper rotor or shaft is 200 millimeters in length with sectional diameters of 20 millimeters, 25 millimeters and 32 millimeters. The diameter near the shoulder of the 20 millimeter section has a slightly larger diameter to incorporate the press fit of the copper disc onto the shaft. There are two pillow block bearings made of thermoplastic with stainless steel inserts. There is one 20mm bearing which is a slip fit and a second 25mm bearing, again slip fit. The conducting disc is made of copper, is 180mm in diameter, 10mm thick with a 20mm centre hole and 6 equally spaced 4.5mm through holes. The magnets are N56 Neodymium. There are two of them which are 176mm in diameter, 20mm thick with a 26mm centre hole and again 6 equally spaced 4.5mm through holes. The magnets are axially magnetised, are epoxy coated with an estimated magnetic field strength in excess of 15,000 Gauss. The drive motor is housed in an aluminium case, 240 volts, single phase, 0.75 kilowatt and runs at 2,900 RPM with a torque rating of 2.53 Newton meters. It is an induction motor. The disc brushes are made of carbon copper alloy. There are 3 pairs, but only 2 are used currently. The surface area of each brush is 12mm by 32mm. They are spring-loaded and mounted on 16mm nylon rods. The rotor brushes are made of carbon copper alloy and they were taken from a Ford Transit van's starter motor, fixed to a U-shaped steel bracket and bolted to the mounting block and then fixed to the bracket using tie wraps. The generator output cables are made of copper and rated at 350 amps. The control panel provides measurement of the motor's input power as well as the motor's volts, amps, frequency and power factor. It has meters for measurement of the generator voltage output and generator current output. It provides control of the motor, on and off and speed control with an optional programmable automatic startup facility. There are 2 load switches, 200 amps each, connected in parallel, which can turn an electrical load on and off with a current of up to 400 amps. There is a load bank which consists of 20 0.1 ohm resistors wired in parallel, which can be switched on or off independently, providing a theoretical minimum load resistance of 0.005 ohms when all the switches are closed. The generator ratings turned out to be as follows. The output voltage is 0.468 volts. The output current is 170 amps. The output power is 78 watts. The motor input power at maximum load is 730 watts. And these values can vary with the changing temperature of the brushes. Now, I initially chose to use a steel mounting block bolted to the large steel base plate. The mounting block was a 6mm thick piece of 150mm square steel tubing. I had an 80mm slot cut out of it where the magnets and disc would sit, with room either side to mount 2 pillow block bearings and a motor and the rotor brushes. For the copper disc, to save on cost, I initially intended to use 2 5mm discs bolted together to make a 10mm disc, but eventually found some 10mm copper plate at a reasonable price, which I had made into a single 10mm thick disc, 180mm in diameter. The 2 magnets which fix either side of the disc are slightly smaller in diameter, 176mm, making a 2mm difference at the rim. The magnets have a slightly larger diameter hole in the centre so that they are not in contact with the copper shaft. The disc and magnets have 6 4.5mm matching through holes in order to fix the 2 magnets and copper disc together with small 60mm long fixing bolts. The magnets are epoxy coated, which provides electrical insulation between the magnets and the conducting disc. The brushes for the copper shaft were taken from a Ford Transit van's starter motor, which is rated at 2.1 kilowatts and means that at 12 volts, the brushes are capable of carrying up to 175 amps. There are 4 brushes, which when used to start the vehicle, 2 are normally connected to the positive battery terminal and the other 2 connected to the negative terminal. This means that each pair of brushes can carry up to 175 amps. Now in the N machine application, the brushes are not putting current on and off the shaft via a commutator, as is the case with a starter motor, but are on a solid copper shaft. Therefore, all 4 brushes are carrying current onto the shaft. This means that they can be commoned together, and the 4 brushes together can therefore carry a current of up to 350 amps from the copper rotor. 350 amp rated copper cable was used to carry the current to the rotor from the control unit and to carry current from the disc brushes to the control unit. So the machine is designed with a maximum capacity of 350 amps. Not long after I decided on the steel mounting block, I realized that using steel could be problematic. The strong magnets would pull towards it, and this would present a significant braking force, slowing and hindering the rotation of the discs. So I decided to scrap the metal block and build a mounting block out of wood, raising the height slightly so that the magnets were a good distance from the steel base plate. I drilled holes through the wooden mounting block and fitted 2 wooden rods through it. These were to provide a structure to fix 2 wooden plates to, which would hold nylon rods firmly in place either side of the disc, so that brush holders could then be mounted onto the nylon rods. I also secured the wooden plates to the mounting block with small brackets. As well as the 2 brush holders either side of the disc assembly, I put another nylon rod underneath the discs using small metal brackets, thus allowing up to 3 pairs of brushes to be connected to the conducting disc. It turned out that the 3rd pair of brushes was not needed, and the device worked fine with just 2 pairs either side of the rotating disc. When I got the magnets, I determined that they were having an effect on metal at a distance of 230 millimeters. Therefore, the steel base plate would possibly still slow down the rotation. So I decided to increase the size of the base plate by adding a wooden section made out of scaffolding planks and bolting it on top of the steel one, thus raising the height of the mounting block so that the rotating magnets were further from the steel base plate. This made the base plate heavier and more sturdy. In order to monitor the various parameters of the machine, a control box was needed. This was in preference to the usual lab setup where various instruments would be strewn across the lab bench with wires everywhere in an untidy fashion. I wanted to keep the design modular so it could be easily disconnected and moved to different locations. So the control box would house all or most of the necessary instrumentation. Now at the start of the project, I wasn't sure how powerful the drive motor would need to be to turn the machine. So I started off with a fairly small, inexpensive motor, hoping that it would be able to run the machine at the required speed, but expecting to possibly have to upgrade it. Having looked at various motor types, I was very interested with CNC spindle motors. These motors can go up to very high speeds, well over 10,000 RPM, but do not have a particularly high running torque. The high spindle speed and speed control attracted me to try this type of motor, as achieving a very high speed would produce a much higher voltage output from the generator. The first motor was a 3-phase pulse width modulated 400 watts spindle induction motor. Note that the 3-phase is produced using power electronics by pulse width modulated DC and not by a standard 3-phase power supply. This motor turned out to be not powerful enough to turn the generator. I'm just going to start it up, run it at a slow speed. So that's running just over 1000 RPM, and you can see it's drawing 160 watts. Just zoom in on that. 158 watts. Right, if I increase the speed a bit more, (2000 RPM), It's just over 200 watts. So half the power of the motor is being consumed in overcoming the friction of the bearings and these brushes. And we haven't even got the disc brushes fitted yet, and I would imagine that they're going to generate more friction. So it's probably going to push it over 400 watts, and that's the power of the motor. So I'm pretty sure I'm going to need a more powerful motor. So I acquired a larger 1.5 kilowatt CNC spindle motor, capable of a speed of 24,000 RPM. The 1.5 kilowatt spindle motor came with quite a sophisticated electronic inverter control unit, which can be controlled using external input controls. I wired the drive unit's power supply and some of the control signals through my control panel so that the input power could be monitored and so that the control panel could be used to start, stop and control the speed of the motor. Right, I've moved the generator again because it was getting right on my nerves. It was getting in the way when I'm trying to build stuff. So we're in the studio now, and I managed to get these controls working with the inverter control unit. So I'll just show you that. You can probably hear the motor, but I don't know whether you can see it. I'll give a close-up in a minute. And this is our 10-turn speed controller with, as I said, this speed controller here, one turn and then you right up to 24,000 RPM. But with this one, because it's 10 turn, it gives a very fine adjustment. So we're running 100 hertz on there, is that's 6,000 RPM it's going at there. So about okay. I tested the spindle motor with some dummy 5 kilogram discs to see if it had enough torque to move the heavy load. In order to get it to start, I had to set the spindle motor's speed set point to 20,000 RPM in order to create enough torque to get it to start moving, but then quickly move the set point down to a safe level as it picked up speed. This was fiddly and possibly dangerous because if care was not taken, it could easily send the generator into a dangerous speed. These motors gather speed very quickly, and if a set point is set too high with the manual speed control knob, it could result in a speed that would be disastrous and wreck the generator and probably the house. So I added some control circuitry inside the control panel in order to safely control the speed set point of the motor, such that the motor could be started automatically without exceeding any dangerous speed. To do this, I installed a Raspberry Pi Pico microcontroller and wrote some startup sequence software which automatically sets the speed set point, starts the motor, then ramps the set point down uniformly over a safe time period in order to arrive at a consistent, repeatable starting speed. However, once I got the generator assembled, it was clear that this motor was still not quite powerful enough. The motor could run the machine, but not produce enough torque to start the machine with all the brushes connected. And when it was running, it was getting quite hot and drawing more power than its rated power capacity. So I changed tack again with the motor and went for a standard single-phase industrial induction motor, which has a torque rating of more than twice that of the spindle motors, although still only rated at 750 watts. I cut a piece out of the mounting block and fitted additional brackets to accommodate the larger motor. This motor turned the generator without any issues up to its rated fixed speed of 2,900 RPM and could retain this speed for long periods. Speed control was not required for this motor as its maximum speed is only a fixed 2,900 RPM. I installed additional input and output sockets to direct the motor's power so that the power could be monitored by the control panel, and added a simple 30 amp rated start-stop switch to start and stop the motor. This motor runs at an approximate input current of 3 amps, but has a 30 amp startup current. So I added a dedicated 32 amp socket outlet in the house to power it. Unfortunately, this motor's maximum speed is only 2,900 RPM, but at that speed the generator produced an output voltage of 0.468 volts, which is not bad for a machine of this type and was enough to be able to carry out tests. A faster motor could be used, but I felt that using a faster motor would be considerably more dangerous and that 0.468 volts would be enough to be able to test the machine for the alleged phenomenon. I used varying thickness plastic sheets to make sure the bearings and motor were aligned at the same height. I added a housing at the end of the generator in which I could place a handheld frequency meter. This device uses a laser to measure the actual speed of the generator in RPM. The white mark on the outer magnet is used by the meter to count the rotation and calculate the speed, which is displayed on the LCD display. Okay, the unit has been reassembled and the magnets are running much truer. The gap has been closed between the magnet and the disc, and I've tested it and I've had it running at 2,910 RPM. Okay, let's go. One final test and then tomorrow hopefully I'm going to connect the load. So let's go. Right, so it was 702 watts, which is within the range of the motor. It did go higher than that, but it does that when it starts up. But it was quite fixed at 702 watts, which is within the motor's capacity, which is 750 watts. So the homopolar generator is now fully working, and hopefully I'm going to get some results out of it very soon. So I'm celebrating. I'm going to consider power in versus power out. The claims made by Palma, Trombley and others are that when electrical power is generated by this type of generator, an amount only equal to around 1/5 or less of the electrical output power is required at the input power to produce it. Such devices are usually driven by an electric motor, and the motor connects to the homopolar generator via a rotating shaft, as is the case with my machine. So the power being delivered to the generator is in the form of mechanical power, which can be calculated as power equals speed times torque. Torque is the amount of turning force that the motor produces, and the speed is the shaft's rotational speed in revolutions per minute. When the generator starts putting out electrical power, what is expected, going by conventional physics, is that the torque on the shaft increases. This is known as back torque, and hence to maintain the same speed, the motor input power has to increase to account for the electrical power being generated. If De Palma and Trombley's claims are true, the amount of back torque created when the electrical power is generated would only be about 1/5 or less of the value predicted by conventional physics. Here is a statement by Bruce De Palma. Electrical loading of an N generator produces an internal torque between the conducting electrical disc and the attached ring magnets. However, since they are firmly cemented together, this torque cannot escape from the machine and load the drive motor or engine. Now, in a normal generator, not an N machine or a homopolar generator, the back torque is caused by an interaction of the magnetic fields of the rotor, which is rotating at the center, and the stator, which is fixed. In this device, there is no stator, so it would seem that there is nothing for the rotor to push against in order to generate the back torque. The back torque, De Palma points out, is a torque between the disc and the magnet, which in this case are fixed together, similar to when you're trying to screw the lid off a jam jar. So how does a torque, which is a twisting force between a disc and a magnet that are fixed together, transfer itself to the shaft? Well, my opinion on this is that the twisting force, or the torque, is not between the conducting disc and the actual magnet itself. I think it is between the conducting disc and the magnetic field that the magnet has caused, which in the last video I described as modified space. and I think that can be considered as being a separate entity from the magnet itself. So if the copper disc was pushing against space, not the physical magnet, then that torque would be transferred to the shaft which the copper disc is attached to. Let's look at the power going in and out. In the diagram, we have a motor which is driving a shaft connected to the homopolar generator. If we consider the power going into the device, P input is the power put into the motor. No motor is 100% efficient. The motor I am using has a full load efficiency rating of 77.4%, so not all of the input power measured will be transmitted through the shaft. We can represent this loss of power as P losses 1. When electric current is drawn from a homopolar generator, electrical connections have to be made with the central spinning rotor and with the rim of the spinning disc. This means a solid electrical connection which can carry a large current has to be made between things that are moving at a relatively high speed. To achieve this, brushes are used, although the brush does not normally look like an actual brush. In our case, it is a solid block of carbon-based material containing copper to improve conductivity. In order to create a good electrical connection which can carry a large current, the brushes need to have a significant surface area in contact with the rotating parts and be pressed against the moving surface with some force provided by a spring. This force presents a frictional load on the generator which must be overcome by the torque of the motor. This in turn means that considerable power is consumed by the brushes. The bearings also consume power, but far less than the brushes. If we say that P losses 2 is the amount of power consumed by the generator brushes and the bearings, etc., this can be considered separate from the electrical power output, which we will call P output. In my generator, P losses 2 is large because I am using carbon-copper alloy brushes, which present a considerable burden of friction. These brushes were used to keep the cost and complexity down. Liquid metal brushes can be used, but to engineer such a generator would be outside of my price range and would be technically more difficult. Both De Palma and Trombley did use liquid metal brushes in some of their machines, but not all of them, and I will come on to that. Having ran the generator, I found that P losses 1 plus P losses 2, i.e. the total losses in my machine, are in the order of 8 times P output, the output power. So there is no chance that this particular machine could ever produce more power out than in. However, once these additional loads are taken into account, if an over-unity effect is present, it should be observable. This can be done by running the generator with no electrical output being withdrawn, then measuring the input power, then loading the generator to withdraw electrical power, which will cause P input to increase by an amount, let's call it P extra in, and comparing that additional input power, not the total input power, with the output power, P out, to see whether or not the withdrawal of electrical power is fully reflected in the additional input power, P extra in. My machine can generate up to around 80 watts of power, therefore it should be possible to switch this electrical output on and off and measure the change in input power, P extra in, to see if the machine's input increases by the same amount or increases by a much lower amount as claimed by De Palma and Trombley. So if this effect is valid, how might it have been overlooked by those who have built such machines? There are a number of things to point out here. It usually comes as a surprise, even to physicists, when you tell them that a co-rotating disc and magnet fixed together produces power. This is known as a one-piece homopolar generator and is sometimes referred to as Faraday's paradox. In some of the online articles that I have read, it suggests that Faraday's paradox had almost been forgotten about until Bruce De Palma rediscovered it and started investigating it. The vast majority of generators are not homopolar generators. You cannot buy them on Amazon, for example. I don't know what the percentage is, but it is a very tiny percentage of generators that are made this way. usually for specialist applications that require a high blast of electric current. And the homopolar generators that are made do not usually use co-rotating magnets, which seems to be a critical element in producing the phenomenon. When I typed into Google how many homopolar generators use co-rotating magnets, what came up first was Adam Trombley's free energy generator patent for his closed-path homopolar generator. Why would they not use co-rotating magnets? Well, I think it's an accepted part of generator design that you have something that moves and something that stays still, and it's the reaction between the two that creates the power. Using co-rotation can add complexity. Electromagnets require further sets of brushes, and permanent magnets are heavy and require more power to spin round than if they are kept stationary. Most homopolar machines have heavy losses due to the power consumed by the brush friction. Therefore, any over-unity type effect would probably not be suspected, because the output power, P output, would always be considerably less than the input power, unless the system uses highly sophisticated, very low friction brushes and bearings, which is usually not the case. When building devices that can be tested on a bench or in a lab, the power output, P output of these devices is usually very small, which also makes the effect, if it exists, difficult to identify in a laboratory setting. Let me give two examples here of experimental co-rotating homopolar generators that have been built and tested in a lab by mainstream scientists. Then I'll come on to the testing of my device. Dr. Tom Vallone, the author of the Homopolar Handbook, who did his PhD on the homopolar generator, built 3 small experimental homopolar generators. He has an open mind and considers the possibility of overunity in his book, which contains articles on Bruce De Palma and discusses De Palma's claims. It also covers some of Edgar Mitchell's involvement. If we take the largest of the 3 generators that Vallone built and look at his results for full load and no load tests, it ran at 1000 RPM and produced an open circuit voltage of 0.065 volts with the drive motor consuming 249 watts. With a load connected, it produced an output current of 380 amps, and the drive motor power increased to 266 watts when the load was connected. So we can use Vallone's test data to look for an overunity effect. When the load was connected, the power input went up by 266 minus 249 watts, which is 17 watts. And his machine produced 0.065 volts times 350 amps, which is 24.7 watts. So in Vallone's case, P input was 249 watts, P extra in was 17 watts, and P output was 24.7 watts. This looks like 7.7 watts of extra power from nowhere, which represents 45% more energy out than expected. But he dismisses this result as being down to possible errors in the measuring equipment and goes to some lengths to explain this. Here's a quote. Noticing the discrepancy between the 25 watts generated and the 17 watts more demanded by the motor, it is useful to do an error analysis on the motor measurements. The appendix contains an error analysis sheet used for teaching the method to physics students at Erie Community College. The method is also used here. Accepting a plus or minus 1 digit error in the least significant digit of the measurements of the voltage and current for the motor, the relative errors can be calculated. Using the method outlined in the appendix, the relative errors are calculated to be plus or minus 0.75% for voltage and plus or minus 0.5% for current. These seem like small errors, but then we have to add them since V and I were multiplied. In order to convert back to absolute error, we multiply by the value of the total power in watts. The total absolute error is found for each multiplication to be plus or minus 3.3 watts and plus or minus 3.2 watts for each. For the subtraction, which was used to find the difference in the motor demand, most scientists forget the correct method used here. Subtraction loses most of the significant digits and therefore loses most of the accuracy. We have to admit a decline in the number of significant digits upon subtraction, or we are just fooling ourselves. The worst thing that seems to happen again and again in the free energy circles is that the generator output looks like it is greater than 100% efficiency when we ignore error analysis. In this case, we have to add the absolute errors when doing a subtraction to get plus or minus 6.5 watts. This answer actually takes account only of the meter error. Any human error would have to be added to the above calculation. The conclusion from the above analysis is that in the 21st to the 1st 83 test, where the open circuit and closed circuit power consumptions were subtracted, we came up with only 17 watts difference. However, this calculation has a plus or minus 6.5 watt error. Therefore, when we calculate the output of the generator with 65 millivolts DC times 380 amps DC to get 24.7 watts, the first correction we have to make is to limit the output power to 2 digits, since the voltage and current measurements are reported in 2-digit accuracy, yielding 25 watts. We cannot increase accuracy by multiplication. Secondly, the absolute errors for this calculation also need to be taken into account, adding upper and lower limits to the 25 watts. Then if 6.5 watts are added to 17 watts, we get 24 watts, which is the upper error limit for the motor demand calculation. This is almost equal to the 25 watts that we calculated for the generator output. Therefore, what initially looked like an energy excess coming from the N-machine homopolar generator is actually within the error limits of the motor demand. Under these circumstances, I cannot make claims for free energy as many other N-machine inventors have done. I can only hope that everyone becomes conscious of error analysis, so more truthful science will result. Phew. Now, if I was doing this PhD, I would have sought to get more accurate meters to show for absolute certain whether or not there was any extra energy. His test results do not prove or disprove whether there is any extra energy, but what has made his test difficult to judge is the small output power that his device produced, only 24.7 watts, and this illustrates the difficulty in proving the effect with a basic laboratory constructed generator. If the error in the measuring equipment is 1/3 of the size of your output power, then the device isn't producing enough output power to clearly prove or disprove the effect. My generator can produce 80 watts. Now, I will add here that Bruce De Palma was livid after he read Dr. Tom Vallone's book, because Vallone failed to include the most important piece of independent evidence which seems to back up De Palma's claims, which Vallone was probably aware of. Now, this is a report written by Robert Kinchlow, who was Professor of Electrical Engineering at Stanford University, who conducted tests on one of De Palma's machines, and I will come on to that later. Now, another paper I found from 2012 entitled Homopolar Generators, an Overview, and this describes a prototype machine which is similar to the device that I have built. And this generator ran at 6,000 RPM and produced an output voltage of 0.255 volts and a current of between 30 and 48 amps. This presents an output power of an astounding 10 watts. The power rating of the drive motor isn't given, but that motor looks like it may be at least several hundred watts. So a 10 watt output is a very small portion of the input power. Therefore, it too isn't powerful enough to be able to draw firm conclusions, especially with instrumentation errors involved. This problem is created because of the large brush friction, which I have mentioned. Now, the authors of this paper were not concerned about nor even looking for an over-unity effect, and were probably not even aware of the claim. It does not detail any test where they compared incremental input power to the output power. But the paper does conclude that liquid metal contacts are mandatory to build a high-efficiency machine, which is what both De Palma and Trombley eventually did. So you see my point with the experimental lab homopolar machines in these two examples, which put out a staggering 25 watts and 10 watts, aren't really capable of showing conclusively whether the effect exists, because the instrumentation error constitutes a large chunk of the measurable output. Now, my machine, however, due to the incredibly strong magnets, can produce 80 watts and 170 amps. This represents over 10% of the input power, therefore an effect, if it is there, should be easier to observe.